Electromagnetic resonance spectrometry is based in particle physics. The property of spin, signified by S, is the magnitude of the magnetic moment of a particle projected on the reference z-axis. M subscript S denotes the possible directions this moment can take relative to the z-axis. Spin is quantized, so M sub S may only change by values of plus or minus 1. There are two types of spin particles. Fermions, which follow Fermi-Dirac statistics, have a spin of 1/2, and an M sub S allowed of plus 1/2 or minus 1/2. They include protons, neutrons, and electrons. As you can see, a spin of 1/2 means the projection goes 1/2 up the z-axis. In other words, the particles spin at 45 degrees to that axis. A change of plus or minus 1 means that that phase changes by plus or minus 90 degrees. Therefore, the only two possible orientations are plus 45 degrees for plus 1/2 or minus 45 degrees for minus 1/2. The other type of particles, following Bose-Einstein statistics, are called bosons. They have a spin of 1, where M sub S can be plus 1, 0, or minus 1. The major bosons encountered in nature are photons. Again, as can be seen, the value of 1 indicates that the vector projects fully upon the z-axis. Therefore, changes of plus or minus 1, again 90 degrees, would orient the spinning particle directly up, orthogonal to the z-axis with a shadow of 0, or directly down with a spin state of minus 1. As was previously seen, fermions spin at 45 degrees to a boson. Therefore, they cannot directly interact. In other words, an electron cannot absorb a photon in order to have a quantum transition. You cannot have spin spectroscopy. However, through wave physics, the electromagnetic radiation does interact and form spectrometry. When fermions spin, they spin around a center of mass at 45 degrees to the z-axis. As can be seen here, this motion prescribes a cone through time. For charged fermions, this creates an oscillating electric field through time in the xy plane. And again, through classical physics, an oscillating magnetic field is created orthogonally through the yz plane. This oscillating magnetic field is central to electromagnetic resonance spectrometry. In resonance spectrometry, samples are first placed into a strong magnetic field, symbolized by B, and measured in Tesla, where a Tesla is a SI unit of a volt-second per meter squared of magnetic moment. This external field aligns the magnetic moments of the individual fermions within it. The magnetic moment is symbolized by mu sub L in the z direction, and that is equal to E, the fundamental charge of an electron, 1.602 times 10 to the minus 19th coulombs, U, the angular velocity of the particle as it spins, and R squared, the radius of the photon, divided by 2. The fermions are now roughly pointed in the same direction. However, they are still out of phase, precessing at different frequencies. An electromagnetic field is then applied to the fermions. The electromagnetic field now aligns the precessions so that all of the fermions are now spinning in phase and aligned in direction by the external magnetic field. With the fermions now spinning in the same direction and in phase, the initial electromagnetic pulse is turned off, and a second pulse at 90 degrees to the additional field is then applied. This causes the fermions to flip. They are now forced 90 degrees away from the magnetic field. The 90-degree pulse is then removed and the original pulse is restored. At this point, the strength of the magnetic field forces the fermions back to their original orientation in a process known as relaxation. Since each fermion is a spinning electric field producing a magnetic field, you now have a signal. Because as one magnet, the fermion, physically flips through a second magnetic field, a current is produced, and this current is the signal. Protons and electrons are both fermions, spinning charged particles which can be brought into resonance in a magnetic field. However, every electron is identical as every other electron, and every proton is the same as every other proton. Therefore, one would think every electron would resonate at the same frequency, and every proton would resonate at its own frequency. The reason why one gets a useful spectra out of resonance spectroscopy is due to something called the Zeeman effect. Each fermion generates a magnetic moment, mu sub L in the z direction, which as you saw was equal to the fundamental charge, E, times the rotational speed times the radius squared over 2. This is also equal to G, which is a dimensionless ratio of the nuclear magnetic moment, or the magnetic moment to the nucleus spin, M, the component of the particle spin in the z-axis, which you know is m sub s for an electron, which is plus a half or minus a half. What you may not know is that nucleons also have spins of half. The entire nucleus has a net spin, I. M sub I is the possible states relative to the z-axis for the entire nucleus. M sub I can span from plus I to minus I. When placed in a magnetic field, as you know, one magnet will attract another, and it requires energy to separate them. This energy is equal to the magnetic moment times the external field B. Since each fermion could have a possible different orientation, plus a half or minus a half for an electron, plus I to minus I for a nucleon, the change in energy between two different particles is equal to the ratio of the nuclear magnetic moment, G, times that change in M times the Bohr magnetron times B. Since M sub S and M sub I are both quantum effects, the change can only be plus or minus 1. Therefore, there is a definite difference in energy between, for example, an electron spinning up and an electron spinning down. This is determined by the ratio of the magnetic moment times the Bohr magneton times B, where delta M winds up being 1. Therefore, since both nucleons and electrons are charged fermions, and both spin and produce a magnetic field, they are not only influenced by the external magnetic field, but they influence each other and therefore change resonance frequencies very slightly to produce a spectrum. We will first look at resonance spectroscopy for the electron. Electron spin resonates in the microwave region with a wavelength of 10 to the minus 6 meters. Repeating, the energy of the attraction between the external magnet and the individual electron is G times the Bohr magnetron times the external field. That change in energy, delta E, as you know, is also h nu from quantum mechanics. Therefore, for any particle, it is easy to determine the resonance frequency, G times the Bohr magneton times the strength of the magnetic field divided by Planck's constant. As you can see, the frequency depends upon the strength of the magnetic field. Stronger magnets produce higher frequencies and better resolution. However, as mentioned, nuclei also possess spin and generate a magnetic field, where the relationship to the energy is identical, except now you are using the m sub I for the total nucleus spin. This is the sum, essentially, of m sub s for all protons and neutrons within the nucleus, and as mentioned, can change in value anywhere from minus I to plus I. Therefore, each nucleus generates 2I plus 1 different magnetic moments. Hence, these magnetic moments will affect the resonance of the electrons, and each resonance is split into 2 plus 1 different frequencies. This is called hyperfine splitting. The resonance spectroscopy of an electron is called either EPR, electron paramagnetic resonance, or ESR, electron spin resonance. For an example, we will look at the EPR spectra of the electrons attached to a lithium-7 atom in a 1.5 Tesla magnetic field. Lithium-7 has a nucleus spin of 3/2. The electron spin resonance frequency, as shown, is G for an electron 2.07183 times the fundamental Bohr magnetron 9.274 times 10 to the minus 24th ampere meter squared times the variable, the applied field, in this case 1.5 Tesla, divided by Planck's constant 6.626 times 10 to the minus 34th joule seconds. For an electron in this field, we get a frequency of 4.599 times 10 to the 10 hertz, or 45.99 gigahertz, again in the microwave region. So therefore, one would expect identical electrons to resonate at an identical frequency, giving one peak at 49.99 gigahertz for the resonance of the electron. However, the lithium-7 nucleus also has spin, and it has a spin of 3/2. Since spin is a quantized number and can change by plus or minus 1, The m sub I value for nucleus spin can be 3/2, 1/2, -1/2, or -3/2. The 4 different values of the 4 slightly different orientations of the nucleus will produce 4 different local magnetic fields, and the resonance will be split into 4 hyperfine lines. The hyperfine lines are evenly spaced around the main absorption. The spacing between the hyperfine lines is related to the magnetic moment of the nucleus. This is calculated in much the same way as in exactly the same way as the magnetic moment of the electron or any other particle. The difference being we use the G factor for lithium-7, 2.17098, and as a nucleus is much larger than an electron, its field is actually smaller, with a nuclear magnetron of 9.66 times 10 to the minus 27th ampere meter squared. As mentioned, this gives a frequency of G times mu sub n over h. With a smaller nuclear magnetron, you have a frequency difference of only 0.032 gigahertz. Therefore, again, the spacing between each of the lines will be 0.032 gigahertz on either side of where the main absorption would be. Also, the sum of the area under each of these hyperfine lines equals the total area of the main absorption. ESR is used to determine the local environment of a nucleus in a compound. Normally, the nucleus of some sort of metal in an organometallic or a bioorganic material.